Well, folks, this is the very last recitation video, the very last section in this class, 9.1 Fundamentals of Hypothesis Testing. So we're going to understand what hypothesis testing is, the basic structure, null and alternative hypotheses, how to determine possible outcomes of a hypothesis test, and how to decide among those possible outcomes. So let's say we have a product called gender choice that claimed to increase a woman's chance of giving birth to a baby girl from the usual chance of about 50%. So you take this drug and supposedly you have a higher probability of having a girl as opposed to a boy. So how do we test if this is true? Well, what we could do is we could do a classic experiment where we have one group who take gender choice and we look at how many baby girls they have. And so we would expect to see significantly more baby girls, more than 50% for those who took that drug. So just kind of a visualization. We've got gender choice, increase the likelihood of a baby girl. If it's true, then we would have more, significantly more than 50% with baby girls. And if it's false, we would see about half having boys and half having girls. So what's significantly more? Well, let's say that we found out of 100, 52 of them had girls. Probably not good enough, but if 97 out of the 100 had girls, we'd say, oh yeah, very, very effective. But what happens if we have like 64? Is that significantly more than 50%? Here's where we have to kind of think about that a little bit. So in statistics, we answer these questions through hypothesis testing. Consider a sample in which there are 64 girls among 100 babies born to women who use the product. We begin by assuming that gender choice does not work. And so in which we expect to get 50% of the girls among the population of all births to women using the product. We use this assumption to calculate the likelihood of drawing a random sample that differs from 50% by at least as much as the ones that we observed. So in other words, we calculate the likelihood of drawing another random sample in which 64 or more of the 100 babies are girls. If we find that such a sample with 64 or more girls among the 100 babies, it's fairly likely to have occurred by chance, then we do not have sufficient evidence that gender choice works. However, if we find that such a sample is unlikely to have occurred by chance, then we have sufficient evidence that a product may be effective. Keep in mind that even if we conclude that our sample result for gender choice was unlikely to have occurred by chance, we have not proven that the product is effective. We've only found evidence that it might be effective because there could be other explanations for the same result, that we happen to choose an unusual sample that existed, or there are confounding, in other words, other variables that we did not account for. So suppose gender choice is effective and you select a second random sample, and then it's got 1,000 babies born to the women. Based on this first sample with 64 among 100, about how many girls would you expect the new sample? About how many baby girls would you expect if the sample, would you expect in the sample if gender choice is not effective? So, just adding on another 0. So think about that. So a hypothesis is a claim about a population parameter, such as a population proportion, which we're going to use as a lowercase p, or a population mean, which we're going to use the Greek mu. And a hypothesis test is a standard procedure for testing the claim about a population parameter. We're not going to do the actual calculation, but we are going to look at the outcomes if we were to do these calculations. So we're looking at a population parameter, and the two that we're going to focus on are the proportion or the mean, a p or a mu. There are always at least two hypotheses in any hypothesis test. So in our example, we've got one, the gender choice works in raising the population proportion of girls from 50% that we would normally expect, and two, the gender choice does not work in raising the population proportion of the girls. The null hypothesis, very important concept here, is the claim that the gender choice does not work, in which case the population proportion of the girls born to women who use the product should be 50% or 0.5, or really gosh darn close. Using lowercase p to represent the population proportion, we write the null hypothesis as H sub 0 or H naught, that's the null hypothesis, and in this case p equals 0.5. The alternative hypothesis is the claim that gender choice does work, in which case the population proportion of the girls born to women who use the product should be significantly greater than 50% or 0.5. And the alternative hypothesis is H sub A, and in this case P is greater than 0.5. In this chapter, the null hypothesis will always include the condition of equality, just as the null hypothesis for gender choice example is the equality P equals 0.5. However, the alternative hypothesis for gender choice takes on one of three general forms, and that is the population parameter is less than the claimed value, is greater than the claimed value, or is not equal to the claimed value. Now, in the recitation videos, I cut out the examples, but definitely take a look at 9.1 PowerPoint and study those examples carefully, and we will see examples of less than, greater than, or not equal to. So it's useful to give names to three different types of alternative hypothesis. The less than is what we call a left-tailed hypothesis test, because it requires testing whether the population parameter lies to the left of the claimed value. Then we have a right-tailed for the greater than, because it requires testing whether the population parameter lies to the right of the claimed value. And then a two-tailed, which is what we call the not equal to, because it requires testing whether the population parameter lies significantly to either side of the claimed value. Again, this will make a lot more sense if you look at those examples in the 9.1 PowerPoint. And I added this slide just to, I think, make it a little easier to see the one versus the two-tailed. So the one-tailed, meaning left or right, we've got, in this case, up here an example of a one-tailed on the left there, and then the two-tailed, which is we have the critical region on both sides. So one-tailed, the critical region is on one side, and the two-tailed it's on both. I thought that might be a little useful to kind of see the difference. Okay. All right, so the null hypothesis, or H naught, is the starting assumption for a hypothesis test. For the types of hypothesis tests in this chapter, the null hypothesis is always a specific value. In other words, it's always equal to a claimed value. The alternative hypothesis, or H sub A, is a claim that the population parameter has a different value from the value in the null hypothesis, whether that be greater than, less than, or not equal to. Okay, and I added this slide as well to show you the three types of hypothesis tests. The right-tailed, the left-tailed, and the two-tailed for greater than, less than, or not equal to, respectively. So hopefully this helps kind of make sense of what we're talking about a little bit. Okay, possible outcomes of a hypothesis test. There are two possible outcomes of a hypothesis test. Reject the null hypothesis, H naught, in which case we have evidence to support the alternative hypothesis. And then two, not reject the null hypothesis. Important that language there is not reject the null hypothesis. That's not the same thing as saying accept. Okay, so in which case we do not have sufficient evidence to support the alternative hypothesis. Note that accepting the null hypothesis is not a possible outcome, because the null hypothesis is always the starting assumption. And then this in red here is my wording here. You can never prove your assumption. That's true in math, philosophy, law, statistics, and all the social behavioral sciences. In the last PowerPoint, the last recitation video, I kind of talked about this with the court cases. You never prove innocence. That's not a concept. So we never accept the null hypothesis because we assume that. We either reject or we do not reject. The hypothesis test may not give us reasons to reject the starting assumption, but it cannot by itself give us reason to conclude that the starting assumption is true. You cannot prove your assumption. Consequently, we never conclude that there is sufficient evidence to support a null hypothesis. So let's talk about drawing conclusions from a null hypothesis, or excuse me, from a hypothesis test. We will look at two ways in which making a decision about rejecting or not rejecting the null hypothesis. The first is statistical significance. If the probability of a particular result is 0.05 or less, we say that the result is statistically significant at the 0.05 level. And if the probability is 0.01 or less, the result is statistically significant at the 0.01 level. We've actually talked about this before in a previous section. So the 0.01 level, therefore, means stronger significance than the 0.05 level. Okay, so to recap hypothesis test decisions based on levels of statistical significance, we decide the outcome of a hypothesis test by comparing the actual sample result, whether it be the mean or the proportion, to the result expected if the null hypothesis were true. We must conclude a significance level for the decision. That choice is really kind of arbitrary. So if the chance of a sample result, at least as extreme as the observed result, is less than 1 in 100 or 0.01, then the test is statistically significant at the 0.01 level and offers strong evidence to rejecting the null hypothesis. And then the same statement is just at the 0.05 level, which is the same thing as 1 in 20. Whether we're using the 0.01 or the 0.05 level just kind of depends on your preference or the standards of that field. We like 0.01, but a lot of times we're just going to have to be happy with 0.05. Okay, if the chance of a sample result is at least as extreme as the observed result is greater than the chosen level, 0.05 or 0.01, then we do not reject the null hypothesis. We don't have sufficient grounds to say, okay, this is definitely not by coincidence. Okay, so p-values. P-value is short for probability value. Notice we use a capital P to avoid confusion with the lowercase p, which stands for population proportion. And we are not going to cover 9.2 and 9.3, but you know, you're certainly welcome to read ahead in your ebook and look at those if you want. P-value, or probability value of a hypothesis test of a claim about a population parameter, is the probability of selecting a sample at least as extreme as the observed, assuming that the null hypothesis is true. A small p-value, for example, less than or equal to 0.05, indicates that the sample is unlikely and therefore it gives us reason to reject the null hypothesis. In other words, we're saying if it's you know, less than or equal to that, then this is unlikely to just be a random situation, that it probably resulted because of something. A large p-value, so in other words greater than, bigger than 0.05, indicates the sample result could easily be a coincidence, so we do not have sufficient evidence to reject the null hypothesis. Okay, let's put it all together. So one, we're going to formulate the null hypothesis and the alternative hypothesis, each of which must make a claim about a population parameter, for example, the mean or proportion. Be this done before drawing a sample or collecting data. Always do that first, by the way. Based on the form of the alternative hypothesis, in other words, if it's left, right, or two-tailed, in other words, greater than, less than, or not equal to, draw a sample from the population and measure the sample statistics, including the sample size and relevant sample statistic, such as population, or excuse me, sample mean or sample proportion. Determine the likelihood of observing this sample statistic at least as extreme as the one you found under the assumption that the null hypothesis is true. That's always our starting assumption, is that the null hypothesis is true, and then we try to reject it. The precise probability of the observation is your p-value, and then decide whether or not to reject the null hypothesis based on your chosen level of significance. There are other values other than 0.05 or 0.01, but those are the ones that are most commonly used. And which one you use is kind of just based on the context and what your standards are. Again, be sure to avoid confusion among the three different letters of P. Lowercase p is population proportion. Lowercase p hat is the sample proportion. That's the one that you're observing from your sample that you drew from the population. And the uppercase p stands for probability value. And then in American courts, again, y'all know that I like the analogy of the hypothesis testing with the courts. So the fundamental principle is that a defendant is assumed innocent until proven guilty. Because of this, the starting assumption is innocence. So H naught is the defendant is guilty. The H sub A is the defendant is guilty. And so the prosecutor has to present enough evidence so compelling that the jury is persuaded beyond all reasonable doubt to reject the null hypothesis and find the defendant guilty. The prosecutor does not make a significantly, in the event that the prosecutor does not make a significantly compelling case, the jury cannot reject the null hypothesis and the defendant will be found not guilty. Again, they never find him innocent. They just say we don't have sufficient evidence to say that we can reject the null hypothesis that the defendant is guilty.